Unit 9, Conditional and Indirect Proof. Unit 9 is not a new set of rules, but is actually just two new techniques that help us solve the problems. So unlike Unit 8, where you had to rely completely on replacement rules, in Unit 9, we actually give you two techniques that sometimes can make more difficult proofs actually much, much easier. And in both of these techniques, you're going to make certain assumptions. And these assumptions that things that you're going to introduce into the proof and then use in order to help you get to the conclusion. So again, if you've read the textbook, you might already have an idea of how indirect and conditional work. So what I'd like to do is just go over the basic ideas, sort of highlight some of the rules and restrictions that these two techniques have, and then go over a couple of example problems for you. And then pretty much let you go and work problems from the book. Now, what you're really going to notice is that problems from the previous unit are much, much easier when you have these two techniques. So problems in the previous unit that may have stumped you or that may have gone on to extremely long lengths, 25 or more lines, it turns out that with conditional and indirect, oftentimes you can shorten the number of lines that it takes, or if it doesn't shorten the number of lines, it reduces the number of replacement rules you have to use. So in some ways, it can vary whether or not the conditional or indirect actually saves you time, or whether it just makes the actual steps easier. So it's often the case, for example, with indirect proof, that you will have more lines than you would have had if you relied on your rules of replacement. But the moves that you make are much simpler, are more of the basic rules as opposed to having to use more of the replacement rules. That's not always the case, but oftentimes doing it through, for example, indirect will save you time. Conditional proof also is when we're generally speaking doing it with conditional will save you time and a lot of headache, especially if you don't see obviously what to do. Both of these techniques are really good about finding places to start in the proof, giving you something to start with right away. Conditional proof. Now, the technique of conditional proof is solely for the purpose of creating a horseshoe statement. So if you want to sort of boil it down, what is the outcome of a conditional proof is always going to be a horseshoe statement. It's essentially, as you may have noted from the book, a proof within a proof. So it's saying something like, if I assume A is the case, can I derive C? If I can, then that shows me that A, therefore C, is also the case. So you're making the assumption and then proving that assumption. I think A, therefore C is possible. I'm assuming A. If I assume A, would that lead to C? In such case, yes, it does. Therefore, I've now created this material implication of this horseshoe statement. So you start with the antecedent, assuming it. You prove the consequent or derive the consequent from the other premises within your proof. And then at the end, you simply close off your subproof, your conditional proof, and you write down the horseshoe statement. So let's look at the basic form of the conditional proof. So conditional proof, as I mentioned, imagine you have a conclusion. We'll start with a very simple example. I have my conclusion is P, therefore Q. Right, so standard horseshoe statement. Now it might be the case that I could solve this using my replacement rule. So I could change this, for example, into an OR statement through a conditional exchange, and then look for one or two of the pieces and then add the other. So if I could find not P and then add Q and then change it back, all of these are possibilities. So there's nothing here that says you must use conditional proof. It just so happens that oftentimes it makes the problems easier. So if I'm assuming my conclusion is a horseshoe statement, and I want to solve this, P therefore Q, first thing I'm going to do is assume the antecedent. I assume the antecedent. Then using all of my rules on the lines after that assumption, and I can use any of the premises, right? I can use P just like I would for anything else using modus ponens or modus tollens or whatever. I can use P. I derive Q, and then once I've shown that if I assume P, Q follows, then I'm allowed to write down P therefore Q. Now, there are a few things to note. First of all, you can start a conditional proof at any point within your proof. So you don't have to start it on the very first line that you begin to write. So let's say you have three premises, line 4, you make your assumption. Typically, people will do that. A lot of the example problems will be the assumption will be made right off the bat. But maybe you don't want to do conditional proof initially. Maybe you see some obvious applications of the first 8 rules of inference, and so you want to do those first. That's completely fine. So you can then introduce it after you've done some initial steps. So it's not like you have to do it at the very beginning. So 1, you could start at any point. 2, let me just put that down. You can start at any point in your proof. 2, you must close off your conditional proof. And by close off, we mean this line underneath the Q. So in other words, you cannot solve the entire problem. You cannot assume P, derive Q, and then continue going without closing off and creating this horseshoe statement, writing that down underneath the line. So a conditional proof must be closed off as you complete it. In many cases, this is because you may not be using that horseshoe statement as your final conclusion. So in instances, for example, if you have a biconditional as your conclusion, you might be starting a whole new conditional proof. Right? So for instance, you could say P therefore Q, and then you could assume Q and start doing another conditional proof, where you might end up with P, and then you've got Q therefore P, and then you're going to put those together and then do biconditional exchange. So if your conclusion is a biconditional, oftentimes you may end up doing 2 separate conditional proofs for each half of that biconditional, or what ultimately become the biconditional, each of the 2 halves. So you must close off the conditional proof when you're done. You can't leave that sort of hanging out there without finishing. The last thing is that you can't cross conditional proofs. And what I mean by that is conditional proofs can be embedded within each other. So if I imagine a situation like this, I've got P therefore Q therefore R as my conclusion. Now the setup for that obviously is 2 horseshoe statements, so I'm thinking, well, conditional proof sounds good, but I've got this larger horseshoe statement and I've also got this smaller one. And so one way to do a problem like this would be to assume P and then to assume Q. Solve for R and get Q therefore R, and then close off the outside conditional proof where I get P therefore Q therefore R. So you can embed conditional proofs. You can also do this, by the way, with indirect proof. When we get to indirect, you can do an indirect within a conditional within an indirect. But you cannot cross out one before you finish the other. So if you work in essence, you're working from the inside out. You must close off the inner conditional proof before you close out the outer. So this is not allowed in the system. All right, and so that's what I mean with closing off your conditional proofs. You must also close them off in the right way. You can't have one overlap with the other in this way. If your lines cross like this, then you know you've done something wrong, that you haven't finished your first conditional or your internal conditional proof before you finish the outside conditional proof. The last restriction on conditional proof is the inability to go back inside a conditional proof once you have closed it out. So once I've solved for my conditional proof and I've closed it out, I've gone through and I've said I've got P, I've solved for Q, I closed it, I said P therefore Q. Now if this is line 1 and 2, 3, 4 in here, line 5, on line 6 I can't go back into and use any of those pieces once I've closed off the conditional proof. So you can't go back into a closed conditional proof. Once you close it and you've created the horseshoe statement, that's it. You can't jump back in and use those lines again, anything you've derived inside. As long as that's still open, you can work with those pieces. Now the point of this really is that what you're doing in this sort of sub-proof is proving that if P is the case, Q is the case as well. Right? You're making an assumption and you're proving that that assumption is valid. Once you've closed it off, you're done. That's the only thing the conditional proof does, is sort of substantiate that horseshoe statement, that that's a legitimate horseshoe statement within the proof. Once you close it, you're done. You can then use, of course, 5 in this instance, in the example here. You can use that in the rest of the proof and do anything else you want using replacement rules or the basic rules on it. But you cannot re-enter the conditional proof. So conditional proof, like indirect proof, is really just a tool in your toolbox, right? You're attempting to solve a problem. You're attempting to present a proof. You've tried your 8 basic rules. You've tried the rules of inference, and you realize that you're stuck and say, what do? I need to make this horseshoe statement. Well, now you have a technique to do that. You have another tool that you can use to solve the problem. Again, it's not necessary that you do conditional proof. It's just something that oftentimes simplifies your work, because once you've got that initial assumption, whatever P is, right, that oftentimes will be useful in other parts of the proof. Right, so you'll be able to immediately do a modus ponens or a modus tollens or something like that. So when you have a conclusion that's a horseshoe statement, your first thought really should go to, yeah, maybe I should be using conditional proof for this, just because that immediately opens up a single letter or maybe a series of letters for you to start doing something with. So oftentimes when you're stuck, this is a good technique to begin with. Now, it doesn't change the other rules that I've mentioned, or those tips or hints that I've mentioned. It's still true that you should go through and look for the obvious moves, look for your 8 basic rules, look for a quick De Morgan's move that gets you a conjunction so that you can simplify some things, look for the negated horseshoe statement where you know that you can do conditional exchange, De Morgan simplification. All of those tips and doing your biconditionals early on in the proof are all probably good tips. But after those things, you might still be wondering, how am I going to get this horseshoe statement? And then conditional proof is a nice, easy way to go about doing a number of problems. And as I said, you can also embed conditional proof. So even if you see something that's very complex, that isn't a straightforward P therefore Q kind of setup, P therefore Q therefore R, you have some that even have 3 embedded conditional proofs. And you can also embed indirect proofs with conditional proofs. So those are other possibilities that you have. But conditional proof is just another tool you have for helping you solve problems. So here's an example problem, a nice conditional proof example. And I say it's a conditional proof example because, of course, here we have a horseshoe statement in our conclusion. So it's D there, or A therefore not D. Now, again, I could try doing this problem by doing my other rules of inference and replacement rules. But because I see it's a horseshoe statement and I've got this technique, I'm going to try conditional proof. So the first thing I might do, even before I start the conditional, I might go and say, you know, I'm really want to at least get rid of the biconditional statements. And I see in line 3 also that I have sort of an obvious De Morgan's move. So before I do anything else, before I make my assumption, I'm going to start by doing those things. Now, again, you don't have to. These can all be done within the conditional proof, because in this instance, once you assume A, you're going to solve for not D, close it off, and that's going to be your conclusion. That'll be the last line of your proof. But you can do the other things first. So if you don't initially want to go with conditional proof for one reason or another, or you're not sure if that's the fastest way, or you just see those moves, you want to get them out of the way, that's fine. So immediately I might say A therefore not the quantity B or C, and not the quantity B or C, therefore A. So that's just line 1 by conditional exchange. Then I might do the same with line 2. B therefore D and not E. Put some brackets around that. And D and not E, therefore B. And sometimes just doing this up front, even though you could wait and do it within the conditional proof, also just makes things a little bit easier to see, right? Once you've removed the biconditional, and now you can see the 2 conditional statements, that you have more to work with. And then line 6, I might just say, well, I'm going to go right ahead and do the not E or not A, and that's just 3 De Morgans. Now at this point, before I do anything else, I'm now going to start my conditional proof, because already I see if I assume A, I've got an obvious disjunctive syllogism move with line 6. So there's no point in me waiting. I'm just going to say at this point A, and then my justification is simply assumption, conditional proof. And I draw my line to show that I'm doing a conditional proof. So now that I've got A, if I want to be nice and official. I'm going to do my double negation, 7 double negation on A. Why? Because I want to do that disjunctive syllogism move, not E or not A. Not A is the opposite, therefore not E. So now I've got the not E that I can use in the rest of my proof. So now if I'm going down, I might look again, what other things can I do? What can I do with not E? I don't have a D yet. I've got B, therefore D and not E. So I might think, wait a minute, I've got A, therefore not the quantity B or C, and not the quantity B or C, therefore A, and I have an A by itself. So I see an obvious modus ponens move. So first, I'm going to simplify out A, therefore not B or C. So I've got that first half of line 4, so that's 4 simplification. And I see on line 9 there, I didn't put a justification, so I have line 6 and line 8 is my disjunctive syllogism. So make sure we get that down. So now I've got, going back to line 10 here, I've got A, therefore not the quantity B or C. I've got A in line 7, so that makes for an obvious not B or C. And that's from 10 and 7 modus ponens. Now that's good because I know immediately I'm going to have 2 single letters to work with. And I can see that B is going to come in handy already in line 5 once I simplify out of there. So here, line 12, sneaking in at the bottom here, not B and not C is 11 De Morgans. Right, so now I've got my not B and not C. And this will often happen as you're doing proofs, by the way. If you come to the end of the paper, if you have a very long proof, just draw the line. Make sure we know that you're still doing the conditional. So line 13, I'm going to say not B. I'm going to pull that out. And that's just 12 simplification. And now that I have the not B, I'm looking at line 5, and I say D and not E, therefore B. So in this case, I'm going to do the second half because I can see I got that modus tollens move, right? So if I look at line 5, this seems the side that's going to make more sense for me to use. I don't have B by itself, but I do have the not B, which allows me to do that modus tollens move. So I'm going to go D and not E, therefore B, and that's line 5 simplification. And then again, the reason I wanted to do that was for modus tollens, so I get not the quantity D and not E, and that's going to be from 14 and 13 modus tollens. Now from here, it seems pretty obvious that I'm going to do another De Morgan's move, right? So I've got this quantity. There's nothing I can do with it in that form. But I do notice that I have a not E over in line 9. And so if you look at over at line 9, I've got not E. And when I do the De Morgan's on 15, I'm going to get not D or not E. So 15 De Morgan's. And then on line 17, I've got not D or, and I'm going to double negate just to get rid of those. So I can follow the form of the double negation, or for the form of the disjunctive syllogism. So I'll just do a nice little double negation on that. If you were to skip that, I would not count that wrong. It's clear to see that not D or not E, the opposite of not E is not E, which you have. So again, understanding the form of the rule, that would be all right if you chose not to do the double negation move. I would be fine. But now, just to keep it, completely official, we've gotten rid of those double negations. Just more line here. I've now got not D from line 17 and line 9 disjunctive syllogism. And now that's what I was looking for. So remember, oftentimes as you're sort of seeing the forest through the trees, or the trees through the forest, remember we were looking for not D. I was assuming the antecedent A. Then I had to prove not D. And once I did that, I close off my conditional proof and I say A, therefore not D. And then my justification is line 7 through 18 conditional proof. All right, so it's not 7 comma 18, it's 7-18, because it's all of those lines inclusive are the things that justify that particular horseshoe statement. Indirect proof. Indirect proof shares a similar structure to conditional proof. We will be using the line, the sort of box, and it is a subproof within a larger proof. But indirect proof is a little different. Its logic is essentially much different than conditional proof. An indirect proof is a reduction to the absurd, reductio ad absurdum. Right? The idea is that if I have a conclusion and I assume the opposite of that conclusion, it should lead to some sort of crazy result. So Klenk actually says there are a number of ways you can sort of present the indirect proof. I think your book does a very good job of explaining what the technique actually is. And it says, if you want to prove not A, for instance, and can see no direct method of proceeding from the premises to the conclusion, you can try an indirect proof by assuming A and seeing whether this assumption leads to a contradiction. Now, by contradiction means P and not P, Q and not Q. That's a contradiction. So you want to know whether by assuming the opposite of the conclusion you lead to a contradiction. If it does, your assumption A must be wrong. So in other words, the conclusion of this, presumably you're given premises that lead to a conclusion, not A, and you say, well, how can I prove that these premises lead to this conclusion? Well, one way to do it is indirectly by saying, well, if these premises lead to not A, then if I assume A is true, that should result in a contradiction, into something sort of ridiculous. So if it does, your assumption A must be wrong since it leads to absurd consequences. Thus, you are permitted to infer the negation of what you assumed, namely not A, which is the conclusion that you wanted. So you assume the opposite of the conclusion. Now, when I say the opposite of the conclusion, it's the entire conclusion, not just the first letter in the conclusion. It's the entire conclusion. So you can think of it as putting big parentheses or big brackets around it and putting a big negation in front of that conclusion. You assume that, treat it just like you would any other premise, work with it, find a contradiction, and then if you do, you know that you've actually, that what you, the opposite of what you assumed, the conclusion, must be true. So the basic form of the indirect proof, as I said, looks a lot like conditional proof. So if my conclusion is P, then when doing indirect proof, I would start by assuming not P is the case. I would then use that, just like I would any other premise, along with the other premises in the argument, to find any contradiction. It doesn't have to be any particular contradiction, just any contradiction that you can come up with. Once you find it, you close off the indirect proof, and then you simply write the conclusion, right? The opposite of what you assumed, which is, of course, the conclusion. Now, just like conditional proof, the same sort of restrictions and things hold. You can embed conditional proof or indirect proof within conditional proofs. You can embed an indirect proof within an indirect proof. You cannot go back inside an indirect proof once you close it off. You can't cross indirect proofs, just like you can't do with conditional proof. So in many ways, it shares those similarities, right? The same thing. You must work from the inside out, and in each case, the indirect proof is just finding a contradiction. Now, indirect proof sometimes can be helpful when you have a conditional proof that has a consequent that you're having a difficult time finding. So imagine you start a conditional proof like we did in the previous slide. You assume P, you're working down, you still can't seem to get to R. So one thing you could do is you could say, well, let me assume not R is the case. If I assume not R and I reach a contradiction, then I know R must be the case. And then that would let me solve the outside conditional. So I would, again, using my rules, come up with some contradiction. So imagine that's Q and not Q. Once I've got that, I close off this interior indirect proof. And then I close off my conditional proof by saying, there's the R that I wanted, P, therefore R, and that's through conditional proof. So this is what I mean by embedding an indirect in a conditional. Since you're looking for a single letter, indirect proof is often handy for doing that. Assume not R, show that it leads to a contradiction, that proves that R must be the case, and then I can close off that bigger conditional proof. So this is a technique that you'll often see. Right, you get stuck, you can't find that letter you need, and therefore you just decide to embed the indirect proof. Now, you can also use indirect proof to solve horseshoe statements. So even if your conclusion where P therefore R. I could do this two-stage where I embed a conditional proof with an indirect proof embedded in it. I could also just say, all right, I'm going to start an indirect proof with not the quantity P therefore R. Now, this is what I said about negating the conclusion. When doing an indirect proof, you're negating the entire conclusion, not just throwing a negation outside in front of P. All right, you have to negate the entire thing. Now, the reason this often works is because we know that a negated horseshoe statement is our friend, right? This is one that easily leads to two letters that I can use very quickly. So you can see that not P or R through a conditional exchange, and I have not P and not R, and that means I have not P, not R, and then from there I can use that to find some contradiction, right? So whatever that contradiction might be, it might be R and not R, it might be Q and not Q, whatever it happens to be, and then once I've done that, I can simply write down P therefore R through indirect proof. So the fact that I have a horseshoe statement as a conclusion doesn't necessitate that I do only conditional proof. I could avoid it entirely by trying to use my replacement rules. I could do it with conditional proof, where I assume the antecedent and prove the consequent. I could assume the antecedent, then do an indirect proof just to get the consequent and then put them together. Or I could just start out with an indirect proof. So indirect proof can be used on any problem, on any conclusion. And that's important to remember. Indirect proof can be used for any conclusion. You could do every problem in the book by starting by negating the conclusion and doing an indirect proof. There's nothing that would prohibit you from doing it, regardless of what form the conclusion has. Oftentimes, the two things that sort of hints with indirect proof, if you have a single letter as your conclusion, then generally indirect proof is the way most people will start. All right, so a single letter indicates, yeah, then I might want to try indirect proof. That's one. That's one thing that is sort of a general hint. It's not always the case. Sometimes it's actually easier not to do indirect proof. Now, the other thing about indirect proof that you'll notice is that it generally takes more steps to complete a proof. So indirect proof, when you make your assumption, you negate the conclusion, you start working, generally indirect will have a few extra steps that you might not find in conditional or just using the rules of replacement in your 8 basic rules. But oftentimes it's the only way that you can actually see the conclusion. On the plus side, although it takes more steps, oftentimes the steps you're taking are simpler steps. So you don't have to use as many of the replacement rules if you do this. So some of the replacement rules that might be more difficult for you to see, some distribution moves, or you might miss an exportation or something, oftentimes those are avoided because by assuming the opposite of the conclusion, you already get that one piece that you need that immediately lets you do the modus ponens without having to change something like an exportation or conditional exchange or something like that. So that's indirect proof. Again, this is probably one of the most handy techniques because you can use it on any problem, on any type of conclusion, just by negating the entire conclusion. And sometimes even things that look really messy, for example, if I have a biconditional, if my conclusion is a biconditional statement, even these sometimes can be simplified by doing indirect proof, where you would think the conditional or two conditional proofs might be the way to go. Sometimes it is in fact the case that indirect proof proves to be a simpler way to get to the conclusion, or an easier way to get to the conclusion. Okay, so here we have an example. I'm going to do an indirect proof on this. Again, because it's a single letter, that's one of the indications, especially when you're working on problems from Unit 9. Generally speaking, if you see a single letter as the conclusion, that's really the sort of indicator that you should start with indirect proof. So I'm going to start by making the assumption, the negation, or the opposite of my conclusion. So in this case, I'm just going to assume A, and the justification is the same, assumption IP, in this case instead of CP, because I'm doing indirect proof. Now, from this point, everything you've done in your previous chapters just applies, right? Now you just treat this as any other premise in your proof. So in line 6, I see A, I see line 1, A, therefore B or C. So I get B or C from line 1 and 5 modus ponens. And now that I've got B or C, I look, well, there's nothing I can really do with that at this point. I see a B in line 4, but that's in a horseshoe statement. But line 3 sort of jumps out at me. I say, well, that's a nice simplification move, right? That's going to give me some more pieces to work with. Now remember, at this point, you're not searching for not A. What you're looking for is a contradiction, any contradiction. So the nice part about indirect proof is, in part, you just keep breaking things down until you find two things that are the opposites of each other, right? A B and not B, a D and not D, an A and not A, a C and not A, or C and not C. That's all you do. You just keep breaking things down. So all I want to do is take these longer statements and try to get them into their simplest form possible. So I'm going to simplify out D from line 3 and not F from line 3 also. And now I'm going to take that not F that I've just simplified out, and I'm going to go ahead and do a modus tollens on line 4. Right? So I'm just looking for common patterns. B, therefore F, therefore not B. So 4 and 8 modus tollens move. And now with the not B, I look at line 6 and I say, well, there's B or C. I've got not B, so let me pull out C. 6 and 9, disjunctive syllogism. Now you notice at this point, I don't actually necessarily know exactly what contradiction I'm going to find. So unlike the other problems where I can kind of work my way backwards, when you do indirect proof, it's not always clear what it is you're going to find as a contradiction, right? Because since you're not looking for the conclusion, you're not attempting to figure out which steps lead to not A, you're trying to find those contradictory statements. So it's a little different technique. When I do indirect proof, I might not even worry about trying to work the proof backwards. All I'm trying to do is see the moves that I can do based on what I've now derived. Once I've made that assumption, I start just breaking things down piece by piece. Just keep breaking things down until I come across a contradiction. So with that C, I see in line 2, I've got another modus ponens move. So the question is, why am I doing it? Because I can, essentially. That's the only reason I can give at this point, because I know that if I can just get things broken down in smaller pieces, hopefully I'll stumble across the contradiction somewhere. So on line 11, I might say D if and only if F from 2 and 10, modus ponens. And then I'm going to, of course, do my biconditional exchange here. So D, therefore F, and F, therefore D. And now looking at that, I see I have the not F already. And I've got D, therefore F. So line 13 here, I'm going to simplify out D, therefore F. 12 simplification. And then D, therefore F, not F in line 8. That gets me not D. So 13 and 8, a modus tollens move. And now I see my contradiction, right? So I've got here a not D over here, and I've got D over here. So there I found my contradiction. And so line 15 is I have to write down that contradiction, D and not D. And where am I getting that? I'm getting that from line 7 and 14. That's just a conjunction. And then I close out my indirect proof, and I assumed A, so my conclusion is not A from lines 5 through 15, indirect proof. Now it's possible you could have found a different contradiction, right? There could have been something else. So for example, if I look here at my proof, maybe I saw D over here and I saw D, therefore F. Well, I could do a modus ponens move and get F, and I would have F and not F as my contradiction. So it's possible that there's more than one contradiction that results. And if you don't get the same one I do, that's fine, as long as you get a contradiction by doing the legitimate moves in the proof. But you see here that the indirect proof is a little bit more shotgun approach. Right? You continue to break things down until you run across that contradiction, and you might not get the same contradiction as I do, and that's just fine. As long as you come to a contradiction, remember to close it out, and then just state the opposite of what that assumption was, which is, of course, the conclusion that you were looking for.